Hello, friends. Hoping you're able to find this video and watch it before we have class on Wednesday. Um, I wanted to start off just like with an application of the integral. And then I wanted to do four tricky integrals. And I also wanted to let you know that there is indeed a web work assignment up. It's web work, homework 8, I think, or something like that. And it's on some applications of integration by parts, but maybe not always. So there might be some integrals in there that don't require integration by parts. Not a lot, but there's at least one. So keep an eye out. There's something actually kind of basic in there just to keep you on your toes, which is what we're going to practice being for the rest of the semester, mostly being able to discern what techniques we need, maybe multiple techniques to get an integral knocked out. So anyway, first off with this application that I've got, and it's a very classic physics application. You've got a ball that starts 5 feet off the ground, and we're going to use English units because we're that's the way we roll here. Uh, and it just like kind of makes more, I don't know. I'm old, so feet were ingrained in me no matter how hard they tried to get the metric system off the ground when I was a youngin'. So we've got this ball. It's 5 feet off the ground, and it is thrown upward with a velocity of 10 feet per second. So we've got this upward velocity on it at 10 feet per second. Our question is, we have a couple questions actually. When does it reach max height before it starts coming down? What is that height? And then lastly, when does it hit ground? So like how long is it in flight? Let's set up some things. We're going to assume that time is zero at the moment the ball is released upward. And we're going to let x of t equal its position. I guess we've used s probably back in the day. So s of t equals the position or height at time t. And then v of t is equal to the velocity at that time. And a of t is the acceleration. That's how fast the velocity is changing. So let's think about these things again. In the first off, in the way we thought about them originally. So if I've got position function and I take that derivative, I get the velocity function. If I take the derivative of the velocity, how fast is the velocity changing with respect to time? I get the acceleration function. So now, in terms of the language, that's for a later class. In terms of the language that we're using now of antiderivatives and integration, we could say this a different way, that the velocity is the antiderivative of the acceleration, and there's some constant on that, and the position is the antiderivative of the velocity. Some these c's are not the same. This is going to be our initial velocity. This one's going to be our initial position or height. So we need somewhere to start, and the place we're going to start is with some basic assumptions about how gravity works. So all objects are accelerating toward the center of the Earth at negative 32 feet per second. Well, 32 feet per second towards the center of the Earth, negative 32 feet per second squared. If we're thinking of away from the Earth as being a positive motion, towards the Earth would be a negative motion. So we're going to set that at negative. It's always pulling us downward, is what you can think at that rate. So from there, I've got v of t is the antiderivative of negative 32 with respect to t plus c. So when we work that through, we just get negative 32t plus c. And that's our velocity at any particular time. Now, v at 0 is our initial velocity. And you notice that if I replace t with 0, I just get c. So this is equal to that initial velocity of 10 feet per second, which is positive because it's moving away from the Earth. So that is going to be 10 feet per second. And our velocity function then is negative 32t plus 10. All right, so we got that. Now we're going to do our acceleration function, or excuse me, our position function. So position is the antiderivative of the velocity plus some constant. And that constant is going to be our initial velocity. You'll see that as we unfold this all. So this is equal to, let's get that function that we just created, negative 32t plus 10 dt plus initial velocity. That's our constant of integration here. So instead of a c, I'm just using what I know it's going to end up being. And when I take that antiderivative, I get this t going to t squared. We divide by 2 out in front. The 10 goes to 10t, and then you can see that when t equals 0, we want this thing to be our initial velocity. Excuse me, initial position. Sorry, initial position. Oops. So this is our S naught, which was how high the ball was off the ground, and that was this guy right here. So this was S naught. This was V naught up here. All right, so our position function is therefore negative 16t squared plus 10 plus 5, 10t plus 5. It's pretty sloppy. I'm going to rewrite that just a little bit. I don't like it. So plus 10t plus 5. So now we've got our position function, and we can answer all sorts of questions. But those questions might actually be a little bit easier to answer, especially the first one. How high does the ball, at what time is the ball at its maximum height? And if you think about how a ball moves, it's going to go up and its velocity is going to slow. When it reaches its apogee, its max, you're going to have the velocity at that moment, whatever that is, equal to 0 before the velocity starts becoming negative. So we've got a positive velocity that's decreasing up to velocity that is 0 and then becoming negative as the ball falls toward Earth. This totally syncs up with knowing that we need to find the critical values of S of t, which are the solutions to derivative of s with respect to t equals 0. And so in other words, just when that velocity is equal to 0. So our velocity function is this negative 32t plus 10. So we get v of t equals 0 when negative 32t plus 10 equals 0. So 10 t equals 10 30 seconds. It's pretty fast. It's like a little less than a third of a second before that ball reaches its max height. And I made up these numbers, so that's why it's so stupid. But it is what it is. So what I have to do to find the max height is to plug that time into the S of t. So we want S of 10 30 seconds, which is equal to, let's see, what was our S function? Negative 16 times 10 30 seconds squared plus, it was 10, right? 10t, so 10 times 10 30 seconds plus 5. And I'm going to actually get out a calculator to work this thing through. Part of me wants to just do the fractions, but I don't think we're going to do that. This is all made up stuff anyway. So let's take a look here, calc. And you might be doing this with me. So let's see, I've got 10 divided by 32. I'm going to store that in memory. Isn't this nice how I'm just saying all this stuff to you while you look at that screen that's not moving? And then I'm going to square that sucker. And I'm going to multiply that times 16. I'm going to make that all negative. And then I'm going to subtract off 100 divided by 32. Look at me being all efficient. I'm going to add that on, excuse me, plus 5. And what I get is 6.56 feet. So that ball does not go very high. Remember how it was? I guess we should have thrown it a little faster. We threw it at, what was it? 10 feet per second. I guess we should have given it a little bit more oomph if we wanted it to go higher than a foot and a half above where it's at. So this is just like a little toss. You got it in your palm, you just toss it up like a juggling ball or something like that. And so our max height is this. Now, when does the ball hit the ground? That is going to happen when S of t is equal to 0. So what we have to do is solve for that. And that turns into negative 16t squared plus 10t plus 5 equals 0. And we got some quadratic action here. And I'm going to use the fact that at squared plus bt plus c equals 0 has the solution t equals negative b plus or minus square root b squared minus 4ac over 2a. And that's the quadratic formula. One of those roots is going to be um, the negative time when the thing would have left the ground to get to that initial 5 foot height. And that's not what we're concerned about. We're concerned about the larger positive time after the thing's flown up and come back down. So what we get out of this is negative 10 plus or minus square root of 10 squared minus 4 times 5 times negative 16 all over 2 times negative 16. And now I'm going to get this out again, figure this all out. Well, I'm going to actually do a little simplification here first. So this is negative 1/32 times negative 10 plus or minus square root of 100 plus, that's 20 times 16, so that should be 320. So the square root of 420. And you can see here that the minus root is going to give us the negative answer. So I'm just going to do the plus version on that. So we've got 420, going to square root that, and then I'm going to subtract off 10. Oh, actually, we do want the negative because we're going to divide through by a negative again, and that'll be the larger magnitude answer. Yeah, so I'm going to start this over. So I take 420 square rooted, and then the negative of that. And actually, I'm just going to get rid of all these negatives because they can make this a plus 1/32, a plus 10, and then plus square root. So you can see that the outside negative would cancel. And so I'm going to take that plus 10 and then divide that by 32. And what I'm getting is like 0. So I get t equals, I kind of just want to keep it on this page. T equals 0.95 seconds. And that's our total flight time. From the minute you let it go out of your hand, cast upward, to the time it hits the ground. So there's a problem like that awaiting you on the web work. It's maybe the first problem on there. That's how you'll rock that problem. Now let's take a look at a few interesting integrals. And one of them, we're going to derive a formula, and then you can just look up the other formula for this one. I forget which one um, is in the web work. I'm going to do something I don't usually do and work out a very general formula. So if I have e to the ax cosine of bx, and I want to integrate this, I'm going to try to use parts, but what you'll notice here is that there's no part that will become simpler when I differentiate it. That's okay. We're going to play a little bit of a trick here, which is cool, and I want you to see that. But realize we could never use parts alone without a special technique to get this thing into any nice shape. The cosine's going to go negative sine, and then negative cosine, and then sine, and alternate back and forth. All the while, extra b's will be coming out. If we differentiate the e to the ax, that stays the same level of complexity with more a's popping out in front. So we're gonna we're gonna do parts, but we're gonna be very clever about it. And we're gonna call this whole integral I. And then I'm gonna choose my parts. So I'm gonna let u equal e to the ax, and I'm gonna let dv be cosine of bx dx. And I take my du and I integrate over here to find my v, and that's going to give me a 1 over b sine of bx. And then we use parts. So I is equal to u times v minus the integral, and maybe I can fit it in over here. Scratch that off. Minus the integral of v du. So notice that I've got an a over b that would come out front. Integral e to the ax sine of bx dx. Looks very much like our original integral, but not quite because there's a sine there, not a cosine. But what we're going to do is parts again on this new integral. So on this dude over here, I'm going to follow suit and let u be the e part, let dv be the sine bx part, and then du is going to equal a e to the ax dx, And v is equal to negative 1 over b cos bx. You should think about why that is. Think about why there's that sign change. And so now I'm going to rewrite that integral. And that integral is still all multiplied by a over b. So what we have now is I equals 1 over b e to the ax sine of bx minus a over b u times v. So that's negative 1 over b e to the ax cosine of bx. So that's my uv. And then I'm going to do minus integral v to u. So there's already a minus on the v, and that becomes a plus a over b integral e to the ax cosine bx dx. And then that closes that off. Now notice that that is in fact our original integral right here again. So it's showing up inside of there. And let's rewrite this and simplify. And I'm going to have to come back here a few times after I get a new page. So we're going to rewrite this guy as I equals, and then this was 1 over b e to the ax sine of bx minus minus. So this becomes a plus a over b squared e to the ax cosine of bx. Right, I'm just copying down this little bit here. And then I've got minus a over b times a over b. So that's going to become minus a squared over b squared I. That original integral pattern appears again. So minus a squared over b squared I. So we've rewritten the original integral I in terms of some fancy stuff, some e's and sines and cosines, and then also itself. So here's the cool trick. I'm going to move the minus a squared over b squared I to the left side. So in other words, the left side becomes 1 plus a squared over b squared I equals 1 over a e to the ax sine of bx plus a over b squared e to the ax cos bx. That's looking pretty sloppy there, but that's cos bx. And I'm just about done. I'm going to notice that this thing in the front here, this can actually be written as a squared plus b squared over b squared. And I'm going to multiply both sides by its reciprocal. So I'm going to multiply both sides by b squared over a squared plus b squared. And then that was times this 1 over a e to the ax sine bx plus a over b squared e to the ax cos bx. We'll tack on a plus c at the end. We're not super stressed about that at the moment. Um, so this formula probably could work. I feel like there's something prettier we could do here. Um, yeah, there probably is. Let's take a look. So I is equal to b squared over a squared plus b squared, e to the ax sine of bx I don't know. And I'm actually distributing that thing in the front because I see that the b squareds cancel when I hit this guy. So then I get a over um, a squared plus b squared e to the ax cos bx. Now I feel like something's a little. So I'm just going to go back and check my work really quick. So I did u is e to the ax, and then I du just fine, and then the v's, that all looks pretty good on that first one. And then I got uv minus integral v du. So that becomes that a over b, and that all looks pretty hunky-dory. So then I go do this dude, and kind of the same thing happens again. And so this we're pretty good on. And then I had the minus a over b, and we got uv minus the integral b du. So that just puts that a over b out in front. So, okay. Then we came over to here. I feel like that top should be like a B over there. And let's just check the work that I've got here. Leaving some radio silence here. Apparently, let's see. So that was definitely minus a squared over b squared. Yeah. Hmm. Hmm. I'm gonna pause the recording here for a second. I gotta check this out. It fe it looks okay, but it's not feeling right. So I'm just gonna pause for a second. All right, I found my error. It was miscopying. Notice how this is 1 over b here. And I knuckleheaded that and made that 1 over a, when in fact that should be 1 over b. And this all should have worked out a lot better. So when I do multiply through here, what I get is b over a squared plus b squared there, and a over a squared plus b squared there. So what we get in the end is our formula that the integral of e to the ax cosine of bx dx is equal to, so look at how this is going to go. This is b over a squared plus b squared e to the ax. And I think that was the sine. Yeah. Sine of bx plus a over a squared plus b squared e to the ax cos bx plus c. There is a similar formula for this integral, and you should either try to derive that because it's cool and fun, or at the lowest energy level, look it up in the integral table. But how would I use this guy up here? So if you were given e to the negative 2x cosine of x dx and asked to evaluate that, you just have to identify that a is negative 2, b is 1, and then just plug them into the right side of this formula, and you're good to go. But it's good to always see once in your life where that formula came from. And I keep doing that and keep forgetting to flip this way. So another integral I wanted to take a look at. Now you're welcome to take this one and pause the video for a moment and try that on your own and then come back. So I'm going to assume maybe you're doing that. Give you a second. All right. So this one, and I gave the tip the other day that when there's a natural log in there, you might want to try letting u be the natural log as you do an approach to the integral with parts. But what's dv going to be? Well, the only thing left to be is essentially a 1 dx. There's no 1 there. It could just be dv equals dx. We don't have any other choices. But look what happens when we actually integrate then. We get du, or do parts, work out the rest of the parts, and v is equal to x. So that this integral, when I do the formula uv minus integral v du, it's going to look like this. So v 1 over x dx. Look at that. That is so cool how that cancels. So this is x log x minus integral 1 dx. Again, that's x log x minus x plus c. So that is another one. Look, I actually learned. I learned something. I didn't do it again. So let's take a look at one more here. I've got integral of tangent inverse of 8 over x dx. Oh man, that's a rough one, right? That is a very nasty looking integral. So we're going to approach this in a similar way, and I'm going to say you might want to try this one on your own before I go ahead, before you see me do it. So give that a shot if you want to for a challenge, because that is a tough one. And when you're ready to see the answer, here's that. So we're going to let u equal arctan of 8 over x. And just like in that natural log integral, we're going to let dv be dx. So then du is going to be using the natural log form. It's going to be first the outer part first times the derivative of the inner part, which is 8x to the negative 1. And then v is just x. That's just going to integrate up. I'm going to simplify du here. So du is actually going to simplify to 1 over 1 plus 64 over x squared times negative 8x to the negative second. And that, my friends, is this. There's some fraction work to be done here. And if we do it right, we can save ourselves a lot of misery. That is negative 8 over x squared. So notice how that x squared hits the bottom of that first complex fraction. So we've got negative 8 on top. And then when I multiply through here, I get x squared plus 64 on the bottom. Ain't that sweet? So those are my parts. And when I put those together, we're going to get integral arctan 8 over x dx equals u times v. So that is x arctan 8 over x minus integral v du. So that's an x for the v, and then du is this beast right here. And since it's minus and there's a negative 8, it becomes plus 8 integral. And then we had the v du. And that can be done how? Take a minute if you haven't done that. How do you do that integral? Pause. And if you take a pause and you work on it, you'll hopefully eventually see that this is actually a natural log form, just with a little tweak needed. Notice that if the bottom is x, if u is x squared plus 64, du is 2x. And we've got an x on top. Heck, we could even borrow a 2 from here and change that 8 to a 4. And then that thing is in a perfect form. So this actually is equal to x inverse tan 8 over x plus 4, and since that's a natural log form, natural log of x squared plus 64 plus c. We don't need those absolute value signs on there, but I'm just going to leave them there. And that is how we rock that one. And I did it again. You can't have too many successes. Need to stay humble. I got one more that I want to work for you. And this one is the integral of 1 over x squared minus x plus 1 dx. The very tricky one unless you see what to do here. So the first thing, and this is going to push our algebra, I'm going to recommend you try to complete the square on the bottom. So the x squared minus x plus 1, complete the square and rewrite that as x minus something squared plus something else squared. And what you will get if you do that is that this has to be x minus 1/2 quantity squared plus 3/4 dx. That 3/4 is square root of 3/2 squared. And that's actually going to be a little bit helpful for us um, if we're using substitution in a minute here, or we're using a table or something like that. So next, I'm going to rewrite this thing because if you look in your tables or if you remember your basic forms, we've got a form that looks like this. And that is the arctan form. So the arctan's coming back again. That's arctan of u. But I need to have u squared plus 1 in the bottom. So in order to get that, this is going to take a series of 2 substitutions. My first one is I'm going to let u equal x minus 1/2. Du is dx, so everything is beautiful there. And I rewrite this integral as integral 1 over u squared plus 3/4 dx. Now, I could go grab a table. There's definitely a table version of this thing, but I want to show you how to do it without a table first. Maybe you're pressed. You've lost your table. You're on some fancy math exam and you need to know how to do this. So let's talk about how we could do this guy. I want to get a 1 where there's 3/4. So what I'm going to do is pull out the 3/4 from the bottom there. So this is going to equal 1 over 3/4 integral 1 over 4/3 u squared plus 1 du. Now that looks weird, but if you think about it, like check that out, make sure you see that. I'm going to rewrite that a little bit differently over here. So the 1 over 3/4 is actually 4/3. And then we had integral of 1 over, watch how I rewrite this, 2 over square root of 3. You already saw that somewhere before. U quantity squared plus 1 du. So think about what we had before. Look at how I rewrote it. And the reason I did this is because I'm going to use a new substitution. I'm going to say let u prime be 2 over square root of 3 u. So I'm not doing parts, I'm doing substitution. And then du prime is 2 over root 3 du. So that means that du is equal to square root of 3/2 du prime. And we're going to rewrite this beast as 4/3 integral 1 over u prime squared plus 1, and then the du is square root of 3 halves du prime. This now is that arctan form, so this is 4 thirds. And actually, and then we got this, let's combine the root 3 over 2 and the 4 thirds. And what we're going to get out of that is 2 over root 3. You should check that out. I think that's 100% right. Arctan of u prime plus c, and now we're going to do all our back substitutions. So u prime was this, and u was this. So remember that u is x minus a half. So this is going to be 2 over root, no, shit. I need to, let's see if I can cram it in down here. Let's make this really big. Get out of there. So this is going to be 2 over root 3 arctan of u prime, which is 2 over root 3, and then times u, which was x minus a half. Now there's some more simplification that could happen there, but we're going to be very satisfied that we've left things that way. And this friend is our answer. Now I'm going to go try to clean up the middle of this video where there's a little bit of silence and stuff on that e to the ax cosine bx thing. But that's about it for today. So you have a web work. You should check that out. It's definitely open now. See what you can get done by tomorrow or Wednesday. And I will see you then. Absolutely. All right. Take care. Be well while I stumble to try to find how to stop. All right. Bye.